Good afternoon, everyone. Thank you for taking the time to attend this virtual event to celebrate the completion of the Galician Skyway project. This is a very exciting project for a lot of people, myself included, because people who know me well can tell you that I am a certified aviation fanatic. First, I would like to introduce myself. I am Javier Calderón, Director of Enterprises and Business Organization at COE, which is a job that I love. But if I can tell you a secret, my dream job when I was a child, to be a pilot and fly Boeing jets, just like my father did. Which is why I'm very honored to welcome Eduardo Carrillo, Strategy and Business Operations Director of Boeing Research and Technology Europe, and Larry Lee, Portfolio Manager of Boeing Research and Technology, who are here with us today to talk about this very interesting project, which is the fruit of a very successful collaboration between Boeing and the Galician local government. And that leads me to welcome another distinguished guest who is here with us today, Patricia Garay. She is the Director of the Galician Agency for Innovation. Thank you, Miss, for taking the time to be with us this afternoon. And of course, I would also like to welcome our panelists. Thank you, all of you, for being here with us today. As some of you may already know, our main purpose at COE is to help our national government make the best economical and business decisions in order to make Spain a very business-friendly country. So when Boeing got in touch with us to tell us all about this project, we at COE were more than happy to share this information with our members. To date, we have more than 220 sector and regional organizations, as well as a large amount of companies as our members, Boeing included, of course. So without further ado, it's my pleasure to give the floor to Emily Lanton of Boeing to start today's event. Thank you, and I hope you all enjoy this event.
Thank you. Good afternoon. A huge thanks to you, Javier, and to the Confederation of Employers and Industries of Spain, the COE, for hosting today's event. My name is Emily, and I will be moderating and keeping an eye on the time throughout this webinar. As Javier mentioned, we're celebrating today the successful completion of the Galician Skyway project, which has been an incredibly exciting and successful challenge for the Boeing Research and Technology Europe team. We'll be starting with keynote speeches from Eduardo Carrillo, Larry Ley, and Patricia Argueré, before moving on to the technical presentations, which will be divided into three sections. First, communications and cybersecurity from 4:20 to 4:40, then navigation and sensing from 4:40 to 5 p.m, and finally safety and planning from 5 to 5:20. If you have any questions, you can post them in the chat section and we will respond to you in the coming days offline. We will also provide contact details of each company at the end of the webinar. So the time is now 4:06, and I will hand the microphone over to Eduardo Carrillo, Strategy and Operations Director at Boeing Research and Technology Europe. Eduardo.
Thank you very much, Emily, and good morning, good afternoon, and good evening to all the attendees. As I'm aware that we've got attendees from all across the globe. So thank you very much, and also thank you very much, COE, for hosting this event. So just let me share with you a few thoughts about the past, the present, and the next future on this opportunity. So I can recall perfectly beginning mid-2016 when I was part of the first discussion with Xunta de Galicia about this initiative, about the future of unmanned traffic, and I'm honored to be here as part of the closing event of this project. I remember perfectly discussing with Xunta about this opportunity, about these technologies, about the introduction of unmanned aircraft into controlled airspace. And I also can recall perfectly how difficult it was even for us to spot Rozas logo in a map. Imagine translating this information to our colleagues in the States. Now we have more than 150 attendees today, most of them international, and I can tell you, and I bet that most of them can spot Rozas, Galicia, and Santiago in the map. So first, thank you, Xunta. Thank you, Xunta de Galicia. Thank you, Patricia, because you've been able to put and to spot Rozas in the map. And this is simply because your trust and the support that you have provided to this initiative. Coming back to the present, I'm not going to use a lot of time to introduce the technologies. My colleagues are going to do better than me, but just let me talk about people. I mean, this is about technology, but this is mostly about people, the people that have been fighting and working hardly, running the extra mile to make this possible. We've got a great multidisciplinary team from Enaire, INTA, Gradian, Telebes, Centum, and Sodical that have made it possible. I am aware that they have spent long nights to make this possible. So thank you, thank you, thank you to all of you for making this possible. And finally, let me talk about future. I'm sure that you all know that the world is strategic for a company like Boeing that has been pioneering aviation for the past 100 years. And I can tell you, I can confirm you that this initiative is a key strategic initiative for us. We've got the people, we've got the infrastructure, and we've got the support of the regional administration. So I'm positive, I'm optimistic, I'm sure that the future is still to be written and to be discovered. So thank you very much, and congratulations to all of you for making this possible. Thank you, Emily.
Thank you, Eduardo. So next we have Larry Lay, Senior Portfolio Manager at Boeing Research and Technology.
Good afternoon, everybody. Welcome. Greetings from the United States. As Boeing enters our second century, we are focused on the emerging technologies and operational concepts that enable air mobility transformation through the safe integration of unmanned aircraft systems into the airspace. These complex systems must respond to today's and tomorrow's challenges, should be economically and environmentally sustainable, and enable safe air mobility, transportation solutions, and integrated urban and rural airspace environments for passenger, cargo, and service operations. This transformation requires that we must understand, define, and enable beyond visual line of sight flight operations, their rules, and the supporting operational contingencies. This is a key goal of the Galician Skyway project, which is why we are proud to be part of this globally significant and unique test and learn program. The Skyway project advances key technologies, contingency management concept of operations, and airspace redefinition to accommodate the safe integration of manned and unmanned platforms. The project demonstrates the importance and value of close collaboration among government and industry stakeholders and partners to explore and understand these key operational issues. The project advances our collective understanding in contingency management, detect and avoid, autonomous emergency landing, and other key issues and solutions, bringing us closer to tomorrow's future aerospace. Boeing has integrated the Skyway project effort into our global technology and regulatory network. This ensures that our Skyway project team and regional industrial partners understand emerging global customer use space and urban air mobility issues and requirements. Access to this network helps shape our Skyway operational and technology plans and initiatives in advancing the keys to future autonomous mobility, such as contingency management systems and performance-based communication, navigation, and surveillance understandings. However, it is not only a one-way street. Boeing's Galicia and Madrid-based Skyway teams are contributing their growing knowledge and expertise to mobility transformation initiatives with key global stakeholders. Their direct contribution to ICAO's drone-enabled program efforts, India's UTM regulatory policy, and NASA's National Campaign and Vertiport Automation Study demonstrate how the Skyway project team learnings extend beyond Galicia and to defining this new frontier with global customers and stakeholders. In closing, in partnership with the Junta de Galicia and our regional national partners, we have laid a solid foundation of mutually beneficial collaboration. Together, we have moved further faster in defining the key elements of the second century of aviation and in delivering the economic and social benefits of air mobility transformation to the region of Galicia, to Spain, Europe, and the world beyond. Thank you again, and best wishes for a happy holiday season and healthy new year to everyone.
Thank you very much, Larry. It's my pleasure to introduce Patricia Argueré, Director of the Galician Agency for Innovation. Patricia has kindly stepped in on behalf of Francisco Conde, Second Vice President and Regional Minister of Industry for the Government of Galicia, who was unable to attend today. Thank you, Patricia.
Thank you. Thank you very much, Emily. Good afternoon, everyone. Larry, Eduardo, Javier, thank you very much for this opening session. I would like to start, I would like to thank Boeing for the invitation to this closing event in order to share the final results of the Galician Skyway project, a strategic project for the aerospace industry in Galicia with the support of the regional government. Boeing is one of the main industrial partners in the Galician aerospace pole, as you know. And this is why today I want to recognize their contribution so that Galicia can position itself as a benchmark in the unmanned aerial vehicle sector. The work Boeing is doing through leading projects such as Galicia Skyway is undoubtedly a great contribution to meet this objective. It consists of cross-cutting and global-oriented solutions for the whole aerospace sector. Furthermore, we have now a specialized laboratory which we presented 2 weeks ago with the collaboration of the University of Vigo, and this completes a huge set of training activities and other initiatives in the area of scientific and technological vocations. All these activities have had an important effect in the ecosystem and the Galician society. Considering its impact for the consolidation of the Galician aerospace pole and the ecosystem we have created altogether, this project is indeed of great importance for us. Special thanks to the team that has worked together in this project, led by Eduardo Carrillo and all the team. I know that it was extremely demanding, but I am sure that the secret of success was the honest collaboration between people from the consortium. Thanks to each and every one of you. Positioning for the economic recovery is, in short, opting for emerging sectors such as aerospace one. Galicia is already doing it by relying on public-private collaborations, and by integrating its entire innovation ecosystem. This is the way in which we want to access European funds in the context of the Recovery Plan for Europe, which brings us a great opportunity to boost new initiatives in the aerospace industrial sector. And this is how we have constructed this great Galician Skyway project. I'm sure that it has been a very important milestone for Galicia. And I want to finalize my speech by reaffirming my gratitude to Boeing for leading this initiative and for continuing to trust in Galicia. Thank you very much to all of you, and I wish you enjoy this event. Thank you.
Thank you, Patricia. So now we've had an introduction to the project. Let's take a look at the team in action. I'm going to share a video now. Bear with me for a couple of seconds.
How do piloted and autonomous passenger and cargo air vehicles safely share the airspace of tomorrow? It's a question that Boeing and our research partners are answering now in Galicia, Spain. The Galician Skyway project has identified 5 key technologies that must be solved for a future ecosystem where traditional aircraft and UAVs coexist within an airspace. As part of the Civil UAVs initiative, together with national and local research partners, we are developing and testing these key technology solutions to ensure redundant layers of safety at the pioneering Rosas Airborne Research Center in Lugo, Spain. Detect and avoid. Power assurance. Autonomous emergency landing. Communication security. Navigation solutions. But this project isn't just about technology. The development of an aeronautical industry in Galicia is a government priority, leveraging research and development to guarantee competitiveness of the local economy in an inclusive and sustainable growth model. And the Skyway project has contributed to socioeconomic growth in the region through partnerships with local industry. Launching the Newton Rooms STEM education concept in Lugo, providing educational sessions to over 1,000 students and members of the public. Hosting drone days at Rosas Aerodome for local school children. And through a partnership with the University of Vigo to drive aerospace technology in Galicia through direct cooperation between the university and industry. The Galician Skyway project. When we partner, we succeed.
Great. Well, I hope you could all hear and see the video. We're going to move to the technical presentations now. So I will hand the mic over to Skyway Project Manager Ernesto Valls.
Hello, can you hear me, Emily?
We can, yes.
Okay, thanks. Can you share the presentation, please? So, okay, Emily, thanks. Okay, thanks everyone for joining this meeting to hear about the Galician Skyway project. So I'm going to start by giving you an overall view of the project by presenting the big numbers that you see in this slide. A few years ago, our customer, the Galician government, put in place the Civil UAVs initiative with the objective of developing an aerospace pole in the region through the integration of autonomous vehicles in the Galician society. In this context, and thanks to European funding, the Galician government launched a call worth 5.4 million euros to develop contingency management solutions for US. Boeing and our partners were awarded the proposal, but we had a very tight schedule of only 18 months to complete the whole project. During this time, around 100 people were somehow involved in the development of the project. Most of these people come from the companies you see in the center of the slide, which are our partners. We have 3 local companies involved, which are Gradient, Centum, and Televes, that contribute to telecommunications and artificial intelligence technologies. We have also 3 national organizations, ENAIRE, which is the Spanish air navigation service provider, INTA, which is our National Aerospace Institute, Soticol, which is a technological company from Madrid. Along with these 6 companies, we have also been working with some research centers, such as the University of Vigo, the University of León, and the University of Hanover. During the execution time, we have tried to mature our technologies and solutions using advanced simulations and conducting real flight test campaigns in the Rozas Airborne Research Center in Lugo, in Spain, in Galicia. In parallel to these technical developments, we have provided educational activities in Galicia on the use of civil UAVs. We have carried out some workshops, conferences, laboratories, internships, and we did also the STEM education initiatives we did in Lugo last year. So this is the overview of the project from a management perspective, but if we go to the next slide, Emily, please. Maybe here we have a more technical view of the project. This slide summarizes some of the solutions and technology that we have addressed in the project. I'm not going to go into the details because my colleagues will explain further in their technical presentations, so these details. So here I just want to show you how we have arranged the technologies in 3 groups to facilitate later panel discussions. So we are going to have 3 panels. Communication and cybersecurity will be explained in the first technical panel. In this panel, we will talk about the solutions we propose to make the communications between the ground control station and the aircraft safer and more robust during a US mission. The second part is for the navigation and sensing solution. Here we will give some details about enhanced navigation and detect and avoid technologies. And the third panel, finally, we talk about the flight termination and power failure solutions, contingency autonomous management, and we will also present the simulation suite that we have developed to test our solutions. Okay, that's all from my side. Now Alejandro Francois is going to present the communications and cybersecurity panel. Alejandro has been Deputy Program Management, and he was involved in the development of these communication technologies. Thanks again for your attention, and I hope you enjoy the presentations. Alex, are you ready?
Yes, I am. Thank you, Ernesto, and welcome everybody to our first technical panel discussion, where we will be covering aspects related to communications and cybersecurity, and hopefully we'll have the chance to review the main Skyway development and findings in these 2 areas. And to do so, I have with me today as a panelist 3 experts. They are Enrique Romae, who is Aerospace and Defense Team Leader at Televes, Emiliano Bartolomé, who is Technical Lead at Boeing Research Technology Europe, and Isaac Ballesteros, who is CTO at Centum Research and Technology. Welcome, guys, and thank you for being here in the panel today. But before we jump into discussions with our panelists, I'd like to go through a few slides to set the scene and provide some context on what we did in the project. I'll try to start by stating the problem that we were addressing in Skyway. In this slide, you can see that we pointed to trending topics in UAVs today, which are the command and control link and the ways to prevent and mitigate its degradation or total loss. And this is, of course, a critical situation which impedes the piloting command, not only to command the aircraft, but also to receive very important telemetry data with information such as the position of the aircraft or the intended route or other contingencies that might be occurring on board. And this is critical not only for the mission, but also for safety, as there are people on the ground and in the air that could be at stake. And then there's a second topic, very relevant, very important as well, which is cybersecurity. And I'd like to make a small comment or statement on that. And it's probably, if there is something worse than losing the link with your aircraft, is losing the ownership with that without even noticing it, because that would prevent the triggering of appropriate alerts and autonomous contingency procedures. So in Skyway, we have developed solutions to secure not only the communication link, but also the GPS navigation, as it is another important threat, as you know, with jamming or spoofing techniques, someone can take control over the aircraft. If you can please, Emily, move to the next slide. Okay, so what have we done in terms of preventive actions? Well, our colleagues from Televes and Gradient, they have been actively developing solutions to guarantee the integrity of the communication and the navigation signals. And more in particular, you can see there in the image that Televes built and validated a state-of-the-art radio frequency link analyzer with very high sampling rate and sensitivity that enable to discriminate whether the signal is being compromised by any sort of shadowing or interference or fast fading or distance fading, and therefore have the appropriate countermeasurements in place. You can see also how we mounted this state-of-the-art analyzer on our fixed-wing experimental aircraft. They also had a ground control monitoring station with a synchronized protocol that was established between the aircraft and the UAV to exchange important link health status data. And we'll see later on why this was relevant. On top of this, and moving on to the cybersecurity, Televes also work on a solution to spot cyber attacks to the communication link, even if the encryption is broken. And this was done at the network level by sniffing and analyzing all the incoming messages, looking into different statistics such as the packet size or the number of packets or time intervals, and also the context to see whether they belonged or not to the right phase of flight. Because, for instance, we shouldn't be expecting network discovery messages in the middle of the flight or things like that. And then regarding navigation signals, then we had Televes and Gradient working together on addressing GNSS jamming and spoofing detection at 3 different levels. From one side, they work on the physical level of the signal, so they digitalize the analog signal to assess power levels, code correlation shapes, and decoding errors. Then they move up a layer to use the navigation data provided by the GNSS receiver itself to check for inconsistencies between the reported velocity or position, or maybe there could be any interference affecting signal power, things like that. And then they move up to a 3rd layer where they check whether the navigation solution reported by the GNSS receiver agree with the other measurements given by other sensors, or was consistent with other measurements from sensors like a barometer or accelerometer or gyroscopes. Please, Emily, next slide. Right, so whenever a link degradation or a loss of link or cyber attack was detected, an alert is sent to what we call a contingency manager. This is something that will be described in our 3rd panel, so I won't enter into detail now. I just want to mention here that basically as corrective actions, we can either decide to reroute the aircraft to, for instance, avoid interferences or reacquire or strengthen the link by, for instance, climbing to a higher altitude. But we can also try to use alternative communication and navigation means. I won't cover the navigation part either, because this will be done in our next panel. So I will just focus on the use of mobile networks as an alternative means to the primary link. And in this sense, our colleagues from Centum, they develop a highly modular computer that you can see to the right of the screen, which was integrated again in our experimental fixed-wing aircraft to monitor and evaluate the performance of LTE technology at high altitudes. The main conclusions that they got is that the quality of the service of LTE degrades with height, and of course, and it depends on the orography and the setup of the particular scenario, whether it's urban or rural or mountainous. And the problem is also that the degradation with height is not something smooth. For instance, they experienced that they lost the signal when they were above 300 meters, but they reacquired the signal at above 900 meters again. We will ask Isaac later where he thinks this happened and if there is any room for 5G to improve it. Next slide, please, Emily.
Alex, I'll just add that you have 10 minutes left.
Okay, I'll speed up. Yeah, so if all corrective actions fail, the ones we saw earlier, the communication link is finally lost or it has been hacked and we cannot rely on it, there are options to mitigate the situation by having the right autonomous procedures on board and appropriate coordination procedures with other space users agreed beforehand. And in Skyway, we envisage and develop a solution for the piloting command to be able to anticipate the autonomous behavior of the aircraft, the contingency trajectory, with full confidence. And to do so, to anticipate the outcome of that, we need to have on the ground the same decision criteria or logic that is on board, but also the same inputs. That it's, for instance, how the link was lost. And this is why it was important to have this UAV and ground control station synchronization. In our final Skyway demonstration, we were able to carry out the hypothetical flight of a UAV in a non-segregated airspace, where we forced a loss of link situation. Basically, we unplugged the radio modem. And in that case, we were able to anticipate the autonomous contingency behavior and forward that to ATC, so they could see that in their ATC consoles next to other traffic, and they could clear conflicting traffic. Of course, this traffic was simulated, but it was still valid for the purpose of the trial. So let's just quickly go through the 1 minute video that we have prepared to summarize this. It's not as fancy as the one that Emily shows you earlier, but it's good to show the effort that we all put into this. So please, Emily.
Procede a directo barco y le llamo para más alto. Copiado, procedemos.
I hope you guys like that. So let's go, Emily, straight to the questions to our panelists. And the first of them is going to be addressed to Enrique, and it's related to the communication control and command link health analyzer that Televes is developing. So Enrique, are you considering further technical developments to this demonstrator?
Can you hear me? Hello?
Yes, we can. Yes, we can.
Okay. Hello. Okay, about the technical. Okay, so indeed, the system developed in Skyway proved to be efficient at evaluating the current status of the link. We are doing this just analyzing the error side, the reset signal. So right now we are working on the evolution of this product, not just to analyze the current status or the current power and link, but predicting the evolution of it in time. This is using data from the aircraft and from the environment. Okay, let's say right now this gap can be filled by adequate route planning based on coverage maps for this given link, but we see great potential for these predictive functionalities in a near future of really automated drone operations. We are referring, for instance, to mesh networks of UAVs. There, the network is very dynamic. The links between neighboring vehicles are constantly changing. So under these circumstances, the aircraft will have to be able to make autonomous decisions to adapt to this scenario. So for this, for Televes is the natural evolution of this loss of link development. I don't know if I answered your question.
Thank you, Enrique. Very interesting answer. So let's move on to the next question, please, Emily. And this one is addressed to Emiliano, and it's related to the simulator and the alerts to ATC. So Emiliano, can the simulator interact with physical entities like a real drone or ATC?
Yes. Yes, the simulator actually it's a simulator, but it's also able to. It has an internal representation of the virtual entities. So if it's an actual aircraft or if it's a drone, we don't care. It's also represented internally. Tracks from the simulated aircraft are typically read from a file because they were pre-recorded because they were part of a test suite, but also they can be computed dynamically because of a flight plan and the physics of the model of the aircraft. But on the other hand, the tracks from a drone are typically received in that ground control station that you showed in the video. And from there, because the ground control station has the ability of using our APIs, it's able to push those positions into the simulator, or because we develop a proxy that is able to, one side, get the information, get the tracks from the ground control station, and then inject those tracks on the simulator. Same happens with the ATC. We have a mix of the real traffic and the simulator, so we can have several aircraft, physical aircraft flying. We can have several that are virtual, and all those tracks are periodically sent to the ATC. One example is what we did with GammaSim, that is the ATC training tool developed by NIRE that is covering the tower, the approach, and the en route. It's also shown in that same video. And in addition to the flight plan, we are able to send also the identifier of the aircraft, the position, the interface. It's able also to send in the contingency information that you mentioned that is going to be covered in one of the next panels. And all that information is displayed to the controller.
Thank you, Emiliano. Thanks for the answer.
You're welcome. Thank you.
Okay, so next question is to Isaac, and it's related to the use of mobile networks as command and control for the aircraft. So, Isaac, what is your assessment on the current and future use of this technology in drones?
Okay, we have evaluated several systems as an alternative to conventional point-to-point command and control communications. And we choose LTE as a reference because it's present all over the world. However, when LTE were defined, drones weren't being extensively used. This is the reason that several engineers did only consider one use case, that is cell phones will always be on the ground, never flying around. So when we try to use LTE beyond these operational boundaries, things work slightly differently than expected. For instance, in contrast to older cellular technologies, LTE uses only a few frequencies, which are shared by everybody located in the same area. This situation makes a signal transmitted by any LTE node, a station, or user equipment a potential interference for the rest of the network. So a strict and precise coordination among every node must be conducted by the network itself in order to prevent loss of connectivity or low quality of service. Thus, when observed from the ground, are somewhat homogeneous areas with blurred boundaries. However, when cell phones are not on the ground, and of course this is the case of UAVs, cell shape varies, turning into non-homogeneous areas. This means that the cell phone starts hopping from one station to another continuously, degrading its quality of service. However, this situation changes with the new cellular generation 5G that is coming up right now, because it has been already defined with drone business in mind. Massive MIMO, beamforming, ultra low latency, very high bandwidth, and so on. So we believe that in the near future, cellular link will be not only an alternative link to control UAVs, but also to support payload connectivity and the whole operation itself.
Excellent. Sounds very good, Isaac. So let's kick the last question, please, Emily. And that's again addressed to Enrique, and it's related to cybersecurity in this case. So Enrique, how close are we to having these detection systems ready for implementation in UAVs with low size, weight, and power?
Okay, so as you said earlier, the development of anti-jamming and spoofing systems is a very hot topic in the field of autonomous vehicles. And what we have developed and demonstrated in Skyway is important because we have proved not only that jamming or spoofing can be detected, but also that we can do it analyzing directly the radio signal in the analog domain. This is that we don't need to perform frame decoding or satellite identification. This opens the door to implementations with lower processing requirements. And this has an impact, of course, in power consumption, but also in size and cost. Regarding the integration, some of these functionalities may not make sense as standalone products, but they might be an enhancement to an existing system in the UAV. This is, for instance, the positioning systems in the UAV should provide higher security than those used in normal systems. They should provide advanced security features like jamming or spoofing detection, and even ways to minimize it, countermeasures like beamforming to know the attacker. So this is also extensible to the loss of link product that we explained in the first question. That if we're looking for safe operations of UAVs, this requires specific communication modules. That's what we're trying to put those functionalities into existing modules and give enhanced functionalities. So these communications modules would have protection against attacks or link losses. That's what we said about the security, the cybersecurity. So the final conclusion that we obtained from the Skyway project is that there's the need of definition of a standard architecture for UAVs that enables interoperability of those systems. The communications module can take advantage of the GPS, the GNSS. The collision avoidance can be supported by the network data. So this cooperative behavior is only possible if those different subsystems are connected and they speak to each other.
Yeah, indeed. And that links very well to our next panels that will be also dealing with these other subsystems, which could be dependent in the future also on communications. I don't think I was planning for a quick wrap up, Emily, but I think conscious of time, I think I will skip that, not to consume more time from our next panels. But before moving on, I would like to launch a quick survey to get your feedback on this topic. So Alvaro, if you could please launch the survey. You guys should be seeing a pop-up here on your screen. Basically, we want to know your opinion about what is the biggest threat to UAS command and control systems that could jeopardize the proliferation of operations. It could be cyber attacks to communications, cyber attacks to GNSS, or poor performance, that is availability, bandwidth, latency, etc., of the different communication technologies such as point-to-point, mobile networks, satellite communications, or finally regulation that could be too restrictive to authorize the use of fully autonomous operations. So if you could please just choose one option and then click submit, we will soon see the results of the survey.
So we should probably go ahead and close the survey now so we don't lose too much time, Alex. You did start 5 minutes late, but yeah, if you could wrap up in 1 minute, that would be great.
Yeah, well, as a wrap up, I just wanted to thank again our panelists and for being here and giving their impressions on the evolution of the command and control and the threats that we have addressed in Skyway. Just wanted to recall that we have looked in Skyway into preventive actions to guarantee integrity of the communications and the ownership of the aircraft and trigger the corresponding alerts if needed. We also looked into corrective actions such as the use of mobile networks, and finally even mitigation actions where the autonomous aircraft behavior is predicted and even forwarded to ATC. And then I picked up 3 good points from our panelists. The first one is the need to predict the communication link status in future more dynamic and coordinated environments, the benefits that 5G will bring, and also how the communication subsystem is linked to others such as navigation or detect and avoid, which we are about to see in our next panel. So without further ado, I'll just hand the microphone to my colleague Marta, who is Navigation and Sensing Solutions Project Lead, who will be moderating the next panel. So Marta, the floor is yours.
Hello, hi to all the attendees, and thank you very much, Alejandro, for your introduction. So in this panel, we will be covering the technologies we have explored within the project of Galician Skyway in the field of navigation and sensing. The 2 main problems we have identified that require the employment of such technologies are mainly 2, the loss of depth of separation contingency and the absence of GNSS signal. The first one mainly consists of detect and avoid problems, so just our solutions must require the detections of the presence of potential intruders, either collaborative or not, by means of embedded sensors like air-to-air radar, ADS-B or cameras. And then we have to develop a proper alerting system in order to improve our avoidance strategies. The second contingency regarding loss of GNSS has been explored. There exist solutions for this contingency, but they have been mainly applied into other environments such as indoor navigation. So in our context, we have developed specific solutions for navigation in GNSS denied environments by means of 3 low swap technologies that give as a result the position of our aircraft. These are the visual inertial odometry, image registration, and the employment of signals of opportunity. Each of these technologies has been developed and assessed separately, but then we have explored the possibility of fusing them in order to obtain such a unique position signal that could lead to the improvement of current navigation systems. So Emily, if you could pass the slide. We will start with the detect and avoid problem. In our project, we have mainly focused on 3 aspects. Starting with the detect problem, our partners Gradient have developed a synthetic vision system. It's mainly a drone detection system based on artificial intelligence, specifically using the convolutional neural network RetinaNet, which appears to be more efficient than other structures. This software has the great advantages of being able to be coupled to low swap electronics, and also the results have proved that it has an accurate detection potential even below or above the line of the horizon, which indeed makes this system very robust for drone detection. If you can, Emily, please turn on the video. No, please, just the video below. We can see an example of the working of this tool developed by Gradient. As we can see, this is a demonstration from our real data taken during our flight test campaigns in Rozas, Lugo. Then, on the other hand, we have developed a tool that helps us to evaluate which kind of alert an aircraft should receive as a function of both the time and the distance to the point of closest approach with the intruder. And finally, our partners have addressed the modeling of different sensors, specifically ADS-B, air-to-air radar, and the combination between camera and synthetic vision subsystem. And then, based on the outputs of these models, they have conducted the fusion of these sensors in order to produce an unique and improved measure that will be employed to fit the alert evaluation module. Now, we move on to the next slide. We will focus on the solutions to the loss of GNSS problem. We have addressed 3 different technologies. The first of them is the employment of signals of opportunity. In this case, our partners, Femtune, have developed a technology in order to achieve a source of positioning signals based on long-term evolution synchronization signals, using both the primary and the secondary. This system has been implemented in an advanced communication racer, which is the one shown in the slide, and it has autonomous SDR capacities. This ACR has also the capability of both recording and generating signals. All the theoretical models employed in this implementation and the software were validated using real data from our flight campaigns. The next approach we want to study was addressed by our partners Gradient, and it consists of an image registration methodology. This gives as a result the global position of our aircraft and is based on a monocular camera. This process comprises 2 steps. First, we initially developed a set of feature points within satellite images, which are extracted by means of machine learning. And then we perform the registration between satellite georeferenced images and the aerial images we are obtaining from an embedded camera in our UAV. As I said before, the result from this step will be the localization of our drone in global coordinates. Once again, these algorithms were validated using our flight test data in Rozas. Finally, our BIR and TE team, we were along this project developing our visual odometry tools. First, we just adopted a pure visual odometry approach, but then we included the signals coming from an inertial measurement unit in order to make it more robust. We perform a preliminary validation of our results using synthetic data comprising satellite images, but then we developed a specific hardware, which is the one we can see in the slide, which was equipped with both a visual and an infrared camera, inertial sensors, and an accurate GPS receiver that will be employed as a ground truth signal for further validation of our tools. All these input signals in the hardware were properly synchronized before the tests. So this hardware was posteriorly mounted on the UAV that conducted the flights, and thanks to this hardware, we were able to acquire the necessary data in order to validate our software. So just as a concluding remark, I have to point out that these three technologies have been developed separately and validated separately as well. But what we aim with this is to conduct the fusion of these three different position signals of different natures and address its suitability in order to improve navigation systems. This will be further discussed in the questions section. So if we move on to the next slide, another technology that has been exploited within the Skyway project is the passive radar. In fact, the objective of this task was to study the feasibility of drone detection using passive radars by exploiting terrestrial digital video broadcasting transmitters. This task was conducted by our partner Sotical, and the results were very promising as we achieved a fully passive and accurate system capable of detecting both aircraft and drones. And also this system was able of giving additional information on the detected platforms, such as their Cartesian coordinates, their distance, orientation, or their velocity. Finally, our partners also developed a man-machine interface in order to monitor both the detection and be able to track the targets. Finally, if we move to the next slide, in order to support the acquisition of the signals of opportunity we mentioned beforehand, our partner Televes has designed and manufactured several types of antennas. Most of them are illustrated in the slide. These include VOR, ILS, DMA, DVB-T, LTE, and also in order to perform the analog conditioning of the signals, they manufacture such boards. And after that, the digitalization of each of these signals of opportunity was conducted. In order to complete the whole procedure, our partners, Televes, designed an SDR, software-defined radio, which is the one illustrated in the figure, which was the responsible to perform the data acquisition from the received signals. All these technologies and devices were underwent a real-time validation in a laboratory environment. So this is the end of my brief introduction to this panel. So we will move on to a question section in which we will talk to several experts about some of the topics we have regarded before. We will start with sensor function in the detect and avoid. And this question will be addressed to Silvia Avallo, which is a multimodal information researcher at Gradient. So Silvia, can you tell us what are the advantages of the fusion data module for the detect and avoid problem?
Yeah, sure. Well, first of all, the fusion data module developed for the loss of separation contingency estimates the target's positions based on information from 3 different sensors, not only from the cameras, but also from the ADS-B and radar. And combining this information, more accurate estimation of position and speed is obtained. Moreover, this module allows to combine information not only from collaborative objectives, but also from non-collaborative through the use of sensors such as radar or cameras. And finally, the different sensors have been modeled according to the RTCA recommendation, and they have been integrated together with the fusion data module in a simulator. And this makes possible to have a lab test, and that's an additional and very interesting advantage as well.
Thank you very much, Silvia.
You're welcome.
So maybe we move on to the next question regarding signals of opportunity. In this case, we will address this question to Isaac Ballesteros, which is the CTO at Centum. So Isaac, could you please tell us which are the conclusions from the results obtained during your flight campaigns?
Well, The main conclusion is that the performance strongly depends on the network that is on ground. For instance, it depends on how many stations are observed from the air and how they are placed on the field. But we were able to fix horizontal position with tens of meter error, sufficient enough to continue with many operations. However, vertical accuracy is not so good. This is because of the fact that all stations lay on over the same horizontal plane, and the algorithm cannot resolve conveniently this problem. But we may solve this by merely fusing the information provided by this module, the one that we developed, with other sources of information such as barometric sensors or any one of the other techniques that were studied on this project, with the aim of fixing a position on a three-dimensional volume. Finally, I would like to remark that this functionality is completely independent of the carrier's network. So we don't need to interact with it, just listening to signals that are broadcasted by every station. You don't need to have a contract with a specific carrier to have this function, and it works with everyone all over the world.
Thank you very much, Isaac, and don't move from there because the next question is also directed to you regarding the same topic. So regarding the applicability of the system, could these results be taken to any other UAV? I mean, in which measure are these results applicable to other platforms?
Well, we designed the solution always having portability and interoperability in mind. With the aim to be installed on board any UAV, regardless if swap and install computational resources. So we built a system architecture framework, software and hardware, that integrates both synergic visions, integrated modular avionics, and software communications architecture. This allows us not only to deploy and remove multiple payloads and applications on runtime upon mission demand, but also to support flight functions at the same time that we are supporting mission function. And doing this safely in the same hardware device, preventing installing multiple computers or devices, just one device for controlling any function of the UAV operation.
Thank you very much, Isaac, for your answer. Now we will move on to enhanced navigation. In this case, we will address this question to Nayara Escudero, which is an autonomy systems engineer at Boeing. So Nayara, what improvements are expected from the fusion of vision technologies for navigation purposes?
Yeah, on one hand, the fusion of the different approaches provides technological redundancy, which is highly recommended for safe operations. And on the other hand, each of the considered technologies have their own advantages and drawbacks. So the main goal is not only achieving a better performance than individually, but also to compensate those drawbacks and extend the operational range of the final solution. So, for example, visual inertial odometry is very good at estimating a relative pose with no previous knowledge of the terrain, but the position drifts over time since it has no absolute reference, and the track can be done during abrupt maneuvers. In the case, for example, of image registration, it doesn't accumulate drift, which is very important because it can be used to cancel the drift of inertial odometry, and it doesn't require additional hardware. But its accuracy depends strongly on the quality of the images, and it cannot be computed as fast as visual inertial odometry. And with respect of signals of opportunity, also doesn't accumulate drift, and a lot of different sources of signals can be used for positioning, which allows a huge operational range of the solution. But by contrast, the estimation of the vertical position is not very reliable, as Isaac said previously. One of the key concepts of the fusion of these technologies is, yeah?
We can't hear you too well. I wonder if we should cut there because it's quite hard to hear you. I think maybe we should move forward. Would you agree, Marta?
Okay, for me, it's fine on my side, as you wish.
Sorry about that, Nayara.
Okay.
Thank you anyway, Nayara. So we have a last question. This question regards the topic addressed about passive radar. In this case, we will address this question to Mariano Gomez, which is the CEO at Soticol. So Mariano, can you tell us, given the passive radar nature of the technological system deployed in this project, and in view of the good results obtained in the operating environment, do you think it could be integrated into other security or surveillance or control systems?
Yes, yes, of course. The passive radar technology used allows our system to be able to coexist in other environments in where different active equipment are working, such as, for example, airports. Anyway, let me explain briefly how our passive radar system works. It should be noted that the passive radar operation principle is based on a set of techniques to detect targets and to estimate parameters using non-comparative signal as illuminators of opportunity, rather than a dedicated transmitter. So it is important. These systems overcome active radar drawbacks associated with the use of a dedicated transmitter and present many advantages such as a low development and maintenance costs due to the use of coach devices, easy deployment, small size, and low probability of interception. So we are using the digital video broadcasting terrestrial signal as an illuminator of opportunity due to their good features. In this case, ultra-high frequency broadcast signals enable the detection of non-line of sight targets through the phenomenon of knife edge diffraction, and improve the detection and localization of low reflectivity targets due to the possibility of acquiring multiple channels. Because of that, passive radar based on digital video broadcasting terrestrial signals, we think that are good candidates for drone detection. Therefore, and due to the fact that our system exploits terrestrial video broadcasting transmitters, it could be also deployed in an urban environment, such as a city, for example, in order to protect specific infrastructures, such as football stadiums, events with a large number of people, etc.
That's great, Mariano. Thank you very much for your answer. Okay. So now we have finished the questions section. So Emily, do we have time for a brief wrap up and a survey, or are we running out of time?
I think 2 minutes, yeah.
Okay, so I will do a brief summary of the things we've seen in this panel. We have addressed the two main contingencies regarding the employment of navigation and sensing technologies, which are the loss of separation and the loss of GNSS. We have studied different approaches in order to detect intruder, obtain secondary position signals, and enhance a reliable navigation in an autonomous way, and also the availability of exploiting the availability of different position signals from other sources. So now, after having a broader view of some of these technologies given by the experts in the fields that have answered our questions, maybe we would like to have some feedback from the attendees by filling the following survey that will be launched, I think now. So this question just regards a little bit your opinion in terms of the proposed solution, specifically in the enhanced navigation section.
Álvaro, ¿puedes lanzar la encuesta? Gracias.
I think we are having problems to see the survey. At least it's not appearing on my screen.
I'm seeing it, and I'm seeing that people are answering, and I will end the polling now so that you can see, hopefully you'll be able to see the results.
Okay.
Can you see now?
No, I cannot see anything. I don't know why.
Okay, let's move on.
Okay, perfect. Thank you all very much. So now I will give the floor to Michael Hart, which is an associate technical fellow at Boeing Madrid, and he will be talking about safety and planning. Thank you.
All right. Thank you very much, Marta, for the introduction. So I'm very pleased to welcome you to the final technical panel discussion. And so in this section, we'll be covering aspects related to safety and planning for UAV autonomous operations. And we'll review the main Skyway developments and findings in these areas. And so let's not waste any time, and let's get started with an introduction to the topics in this session. I'm going to present a few slides to give you an overview of what our objectives were in this project and how we tackled them. And then, as in the previous sessions, we'll then have a short discussion just about them. So in the first slide, this is just, I'm going to state here 4 of our objectives that we had in this area. These are to determine and evaluate the operational impact from the developed individual contingency solutions, many of which we glanced over in the previous sessions. And here we intend to try to understand how they may potentially increase the safety or even enable a novel concept of operations. Also, like the design, we designed a decision-making contingency manager module, which can be embedded on board for enabling autonomy or on ground for assisting the pilot in control. This can combine then with the risk assessment tools, which evaluate the available mitigation solutions. We designed trajectory planning mechanisms, which combine with microweather modeling solutions, all to maximize the predictability in the contingency situations. And then finally, we performed actual flight tests in order to validate the contingency decision architecture and the trajectory replanning tools, and to in addition to the individual technology solutions. So next slide. So regarding the operational impact assessment, here our work began with first conducting hazard identification analyses. We incorporated into those analyses the individual technological operational aids that we're developing within Skyway in order to understand the consequences of those technologies in operations. This work then facilitated the development of individual contingency decision logic solutions, which were primarily based initially upon rule-based methods. Finally, we studied the existing regulatory framework and proposed some example concept of operations as a means of study. In order to verify then these results, we organized several expert sessions, and there we invited air traffic controllers, pilots, security, autonomy, and technology engineers. And so this led to some really great discussions and new insights into effective and safe contingency mitigation behaviors. In particular, we took a deep dive into loss of link and also loss of GNSS contingencies. Here, both ENAIRE, the Spanish ANSP, and INTA, the Aeronautical Institute, played fundamental roles in this activity. Next slide. In the contingency manager development, well, from the very beginning, we were clear on our perspective that all the solutions that we developed should facilitate in some way autonomous behavior. The solutions could still be applied to a remotely piloted concept of operations, And in some cases, this may merely serve to just devise the pilot on the ground. However, it was clear to us that, should a loss of link occur. Oh, by the way, Emily, could you start the video up here in the right corner there? Yeah, that's our simulation. I'll get to it in a second. So in case of a loss of link occur, an onboard version of the contingency manager software module should have the capacity to detect abnormal events and evaluate the consequences on its own health status or environment, and also then make the appropriate decisions, perhaps by minimizing the operational risk and respecting the operational restrictions and procedures. And also, finally, I want to mention that our approach is we chose to be deterministic and predictable. So in contrast to other, perhaps AI-based alternatives. So we're seeing here in this window, well, is a simulation running here. So in our code and in our simulation environment here, we set up a ConOps of a high-speed train line inspection scenario in which a loss of link is suffered midway through the operation. The system is then presented with several different mitigation options, like continue, return to base, perform an emergency landing at a predefined site, or perform a parachute deployment at even in closer, safe, uninhabited drop zone, for example. And here, well, it's perhaps difficult to see, but it's here the operational risk is then evaluated, considering the many factors using risk maps, as we also see below, which could depend upon the population densities, the different cell phone availability, many factors. And then we the minimal risk solution then is selected. Okay. All right. Let's move on to the next slide. So here I'd like to talk about the predictability. So while handling contingencies, and here this is at our Boeing European Center, we have a long history of pursuing advanced trajectory modeling tools, and which permit achieving very high levels of predictability. Also, their concise representation facilitate an easy exchange among all stakeholders. So we worked in this project to advance with these tools, integrate these with newly developed micro-weather models, and we also combined these with our contingency management decision logic and our trajectory risk assessment tools that we developed and I discussed here in the previous slide. So with this integration, we gained high levels of fidelity with what in our when we tested this in our simulation environment. Additionally, stochastic tools enable to predict the uncertainty in the models, which we can communicate to the different stakeholders. So this is precisely what we did in our flight demonstration, in which we tested our loss of link solutions. We communicated from our ground control station directly to the Santiago control tower, where an air traffic controller received our newly predicted mitigation trajectory, representing the updated flight plan due to the loss of link contingency. Also, finally, these same tools have been used to address loss of engine contingencies, where loss of propulsion takes place, and a gliding trajectory needs to be defined, or loss of power contingency, which implies the need to deploy a parachute. So, okay, next slide, please. Our main test platform, you can see here in the lower right, lower left, which is our ALO from Blind to the INTA, National Aeronautical Institute, with a maximum takeoff weight of 60 kilograms and a max payload of 10 kilograms, and has a 5-hour flight autonomy. We use 3 replicas of these during our flight campaigns, with integrating different payloads and communication, navigation, and sensing. We also use some DJI multicopters in our tests. A lot of integration work was needed to accommodate the various antennas, power supplies, supports, visual and IR cameras, separate redundant RTK GPS systems, NVIDIA processing units. And the flight testing was mainly conducted at the Thiar Rozas airfield, as you heard before. This airfield specifically is especially dedicated to UAV development and testing, where there are laboratories, full flight simulation environments that has been deployed there. There's a hangar, observation tower, and a 1 kilometer runway strip. We conducted 4 different flight campaigns there during the 15-month or so project duration, and all including beyond visual line of sight flights. And in our last 2 flight campaigns there during the past summer, we performed flights almost nearly 10 kilometers from the airfield location and validated many aspects of the solutions. So that concludes my introduction. I'm going to then lead on to a few questions to our panel experts. We have here with us from today, Alfonso Romero is an air traffic controller in Santiago. So I'm going to begin with this question. Alfonso, are you there? Hopefully, what are, in your opinion, the necessary elements that need to be put into place in order to permit more extensive UAV operations in non-segregated airspace?
Hi, Michael. Thanks for your question. Hi, everybody. Well, the problem of integrating drones with visual traffic is a difficult one, since drones are very hard to see by an onboard pilot looking out. VFR traffic don't usually fly established flight plans, routes, or altitudes, and that makes any type of strategic deconfliction very difficult or impossible. Sometimes their communications are not standard. Sometimes there are also problems of radio coverage, and they rely upon voice communications to interact with the traffic, with the nearby traffic. This methodology is difficult for an unmanned aircraft, more so if any means of autonomy is desired. For these reasons, we can see that the introduction of a manned aircraft in a non-segregated airspace with certain levels of autonomy will be easier when flying under IFR instrumental flight levels above the altitude where a visual traffic normally flies. This presents a number of advantages. First, a standard surveillance architecture such as secondary radar, as Santiago, and radio coverage can better account for aircraft movements. Secondly, the air traffic controller can play an important role in coordinating air traffic according to established flight plans, IFR, for example, and in avoiding air traffic conflicts. Also, well-established communication protocols exist or will be requested between ATC and all flight platforms. However, we are not there yet. A mature and reliable detect and avoid systems with sensing and communication capabilities equal or better than a standard pilot needs to be on board. The platform should have a GPS backup navigation system, and also robust measures for safe landing need to be in place. Skyway has touched upon a number of these important issues, and in the expert sessions that were held in Santiago. The reaction logic during a contingency is communication capability together with very high levels of predictability of all its actions or all necessary pieces of this puzzle. Just to sum up, Michael, we are not yet there, but I think we are on the right way. Thanks, Michael.
All right, thanks very much, Alfonso. Okay, next question. Here we have Ignacio Vidal. He's an autonomy systems engineer from BRT Europe. Ignacio, can you tell us what happens once the onboard systems detect a malfunction? How do we go from that system alert to a safe landing or a parachute deployment?
Hello, Michael. Thank you for your question. So once a malfunction is detected, the appropriate monitoring subsystem issues an alert, which is then received by the contingency manager. This centralized intelligence is able to react to this particular alert while taking into account the current system state. Then it is able to select the appropriate mitigation actions. If that action implies a change in the flight plan, the contingency manager has the ability to assess several contingency flight plans and select the one that poses the least risk. I can best explain this with an example. So suppose our UAV is flying under normal operational conditions, and then the engine monitoring subsystem detects a drop in fuel pressure and a significant decrease in engine RPM. It interprets this as an engine failure and issues a loss of engine alert. The contingency manager receives the alert, evaluates the current airspace restrictions and the aircraft's capabilities given its current state. Then the contingency manager decides that the best option would be to end the flight. In this example, there are 3 landing site candidates and 2 parachute deployment sites. So the contingency manager performs a trajectory risk analysis for each alternative and selects the one that poses the least risks to surrounding air traffic, ground installations, and people, be it a parachute deployment or a landing trajectory to a safe landing site. We believe the risk assessment capability can be an important tool for maximizing safety in a contingency scenario when the platform is presented with multiple mitigation options. And since the safety evaluation can depend upon environmental conditions or traffic in a non-segregated airspace, their preference may not be entirely clear before the operation. I hope this answers the question. Thank you.
All right, thanks very much, Ignacio. So next question goes to Eduardo Gallo, who's also an autonomy systems engineer at BRT Europe. Eduardo, depending upon the contingency, say loss of engine, loss of link, loss of GPS, are there any differences in the way the aircraft's operation is planned with the objective of maximizing the predictability of the trajectory? What do you think about that?
Thank you, Michael. Hello, good evening, everybody. In case of a contingency, the guidance targets tracked by the aircraft control system do have a significant influence in the resulting trajectory and whether or not the system is capable of proceeding to go on while minimizing the disturbances to its own mission, other airspace users, air traffic control, and even people and infrastructure on the ground. The objective, depending on the contingency, shall always be to allocate the unavoidable uncertainty introduced by the weather into that dimension less damaging from the point of view of managing the contingency. I will now cover 3 different cases. In case of loss of communications, it is possible to fix the flight 3-dimensional trajectory at the expense of freeing the time dimension. In this way, the aircraft will never deviate from its intended route, although it will arrive to any waypoint early in the case of tailwinds or late in the case of headwinds. Air traffic control in this way possesses the best possible prediction of the aircraft position at all times, enabling it to minimize the disturbances to surrounding traffic caused by the need to ensure sufficient separation with the uncommunicated platform. The situation is significantly different in the case of loss of engine, in which the aircraft continuously loses altitude and needs to touch the ground at one of the previously designated sites in order to minimize damages to itself and ground infrastructure. The uncertainty caused by the weather in this case is redirected by means of the guidance modes to both the horizontal position and time dimensions, lengthening or shortening the path to the designated landing point, but ensuring that it lands where intended. Finally, there are other cases, such as loss of GPS, where there is little or no relationship between the guidance modes and the aircraft navigation capabilities. This contingency is approached by means of novel navigation techniques, but all guidance targets are valid. That's all, Michael. Thank you.
Okay, thanks a lot, Eduardo. Okay, last question goes to Zachary from INTA, the Spanish National Aeronautical Institute. He's a systems and electronic engineer there. Hi, Zachary. To collect data and images for solutions to the loss of link and loss of GNSS contingencies. So it was proposed to carry out flights for the ALO up to a distance of 20 kilometers. So can you tell us about how do you go about preparing a flight of this type?
Well, can I be heard? Can you hear me fine?
Yeah.
The first thing that we consider when preparing a type of flight of this type is if we're going beyond the visual range of the airfield, the most important thing is always safety. A flight plan must be made that avoids flying over populated areas at all costs. And that includes solutions and contingency plans for all possible failures that could occur, thereby minimizing the possibility that the airplane could cause harm to third parties. Feasibility study must be carried out that clearly considers all the areas to be flown over, to include all populated areas, all high-density roads, and all restricted zones along each of the associated flight heights. Once this study is approved, a request to segregate the identified airspace is filed with the aviation authority to guarantee that no other aircraft will be attempting to utilize the same airspace at the same time. In our case, since program requirements were such that we had to fly within the TMA of Galicia, and given the particular orography and populated areas of the site, we were forced to design a flight path from the aerodrome to a work area approximately 20 kilometers away. They crossed the A6 motorway. This in turn drove our mitigation plan to ensure that safety would be maintained in the event of a loss of link between the aircraft and the primary ground control station. So faced with the possibility of a loss of link situation, we were required to define a point of no return for the plane's trajectory, which did generate a bit of stress for the flight test. The strategy consisted of programming the flight control such that if the loss of link were to occur before the aircraft reached the highway, the airplane would automatically turn around and return to the aerodrome. However, if the loss were to occur after crossing the highway, the plane could no longer return and have to continue on its flight until arriving at the work area. Then upon arrival to the work area, if the link had still not been recovered, as was mentioned by yourself, Mr. Hart, at the beginning of the section, the plane would automatically go to a designated recovery zone, it would stop its engine, deploy its emergency parachute, which does inflict a bit of mechanical shock and stress on the aircraft. So in an attempt to avoid this type of emergency recovery situation, a portable monitoring station was established in the work area that, while complicating the logistics of the site of the trial, allow us to be able to monitor and command the aircraft in the event of sustained loss of link, while with the main ground control station, thereby making it possible to continue with the flight as planned. In this way, we were able to ensure it would be highly improbable to lose the link of both the main and the backup ground control stations, thereby providing a bit of peace of mind. However, it is still not completely relieving anxiety related to the fact that once the aircraft crossed the highway, in the event of a sustained loss of link, we would be unable to return and would automatically go to the recovery zone, potentially damaging the aircraft during emergency recovery procedures. That's all I have.
Okay, that's great. That sounds, it's interesting. There's a lot of that goes behind the scenes there and setting up a flight of that type. So great. So I'd like to give a thank you to all our panelists today. Emily, what's our what can we do? Do we have time for the survey question, or what's our next?
We're running 5 minutes over time, and it didn't look to be working too well today. So I would say that we should skip the survey question.
Okay. So then in that case, I think we'll just give the floor to Enrique Casado, the manager of the Digital Aviation Services and Autonomy Group at Boeing in Madrid, who would like to make some closing remarks. So you want to take it from here, Enrique?
Yeah, thanks so much. Can you hear me? Is everything okay?
Yeah, we can hear you.
Okay, perfect. Thank you so much. Well, because we are running a bit out of time, I'll be sharing with you just a short message. You know, the main success of this project is basically founded in, in a, I would say, very synergetic and sound environment we have built all together. This is quite important to emphasize that we have collaborated and worked together side by side. And this is basically why we have achieved such really valuable and relevant technical accomplishments. So first of all, I wanted to thank Gain because, Gain puts a clear vision that was basically leveraged by us to provide, specific details about what to achieve at the end of the project. So we are really thankful regarding this vision, and have to say that Gain also has a medium and long-term vision that will bring a lot of partners and new technical developments to Rozas in the future. I'm pretty sure about that. And basically, I wanted to thank also the consortium. And thanks to these very clear goals set by Gain, we were able, as leaders, Boeing Research and Technology Europe was able to define specifically what we wanted to have from the partners or the partners. And I have to say that this is a clear demonstration of the Boeing motto: when we partner, we succeed. So thank you, everyone. I wish you all the best for 2021, which I think it's going to be a very positive year for everyone, and looking forward to collaborating with Gain in the future, and all the partners and future partners in future projects. So over to you, Emily. Thanks, everyone.
Thank you, Kike. So that brings us to the end of today's event. Thank you, Javier Calderon and Alvaro of the COA. And thank you to all of you who have stuck with us for an hour and a half. We hope you enjoyed the event, and we look forward to seeing you soon. Goodbye.
Bye-bye.